So let me demonstrate the up-and-coming project. I looked at the schedule, and it does show one thing about this class. My organization is not so great. The projects are not completely tied to the topics like you might want them to be, because I had a different number of projects than chapters. So anyway, even though there's hash functions here, we talked about these projects before. The next one we haven't done is 401, which is RSA. So I'm going to show you RSA, even though we aren't going to talk in the chapter for about a month about it, but you might as well start learning some RSA. So 401, because RSA is surprisingly easy. And it was the miraculous public key encryption. This was the original one that did it all. And the thing it does is you generate a key. Your key is two numbers, N and E. All right. And so you have a private key, which is D, to decrypt it. And the way you first, you start by finding two large prime numbers. And prime numbers are numbers that cannot be divided evenly by anything but themselves in one, like 7. You can't divide 7 by 3 or 2, but 9 is not prime because it's 3 times 3. Prime numbers cannot be divided by any integer below them other than 1 and create an even number, an integer number. So you multiply those two prime numbers together, and now you have a big number n. That's the key. And the second number, E, is just used to encrypt, and in practice you almost always use the same number for the public exponent. It could be almost anything, but in practice everybody uses 65537. It's just typically what you use for E. So we're going to do this in Python. Let me open up a, whoop, not that. I need a terminal. There's one. All right. So let's just have Python 3. All right. And so here, let me make this fit on the screen. All right, this will do. And we can close that. Close that. All right. So that looks pretty good, except I think this needs to come in. All right, just a minute. That'll probably do. All right, so if I use the numbers 7 and 23, because they're prime, so n is then 161. All right. Now you have to calculate this number, phi of n, which is p minus 1 times q minus 1. You need this in the calculation. So that's going to be 6 times 22, or 132. 100, all right. And now you get the public exponent, and I'm going to use e equals 5. You could use any number in principle, but for these small numbers, I'm using an e of 5. All right, so now 20 times e is 100, which is fine. Now, you're using modular arithmetic. This is the part that often confuses students. When you're doing encryption of any kind, if you encrypt a byte, you want an answer that's 1 byte. You don't want it to get 10 times bigger because you encrypted it. So you work on a ring. So you go around, like, the clock is a ring. You go from 1 o'clock to 11 o'clock to 12 o'clock, and after 1 hour, you're back to 1 o'clock again. You don't hit 13 and 14. And so the rings here in cryptography, you start at 0, and you go up to n minus 1, 132, and then if you add 1 to 131, you call that 0 again. So there's a total of 132 numbers around the ring, and you never leave the ring. That's modular arithmetic. So if I want to do modular arithmetic, you do it with the percent sign. So if I take 100% fin, and fin is 132, that's so that's 100, 131, 132. Let's just do them all. There. So 100 is modular 132, modulus is 100. 131, modulus 132 is 131, but 132 modulus 132 is 0. That's how it works. You're going around this loop. So now we can try calculating multiples of the encryption key, E. So let's try these. All right, so 20 E's is 100, 21 E's is 105, 22 is 110, 25 is 125, 26 is 130, but 27 times 5 is 3. It would be 135, but you've wrapped around at 132, so it's 3 past that point. So you've gone around the circle and skipped 1 and made it back to here. So what we want to do is find the modular inverse of 5. E is the encryption key, and D is the decryption key. And what you have to do is find a number so that D, you're trying to find a value that will give you an answer of 1 here. And so it's up here around the 50s. You can't find it in the 20, but if you go to doubling that, up to numbers that have made 2 complete trips around the thing, you now find 53 times E. So understand what's going on here. These numbers are going to be used to encrypt letters of a message. You're going to encrypt them by multiplying them by E. So they will wrap around. Then you're going to decrypt them by multiplying that further by D. The problem here is there is modular multiplication, but there is no such thing as modular division. So the only way to undo a modular multiplication is to do another multiplication that undoes it. And since E times D is 1, that means that if you multiply something by E and then multiply that by D, you'll get back where you started. So E is the encryption key and D is the decryption key. So that's something we've talked about before. We talked about modular arithmetic. And anyway, so now we can do encryption. So this is Megan here, wants to receive RSA messages. So she calculates with P and Q, calculates N and phi of N, chooses an E, and calculates a D, the decryption key. So she has all this information, but the only thing she publishes is N and E. That's the public key. Now anybody can send her a message with her public key. So if Q-Ball wants to send hi, exclamation point, he has to encode it somehow, and we can encode it with ASCII, so it turns into these 3 numbers. And we can just encode each of those numbers separately, and here's the way you do it. You take x to the E mod n to encrypt. And this numbers you're sending is x, and E and N are the key. So it's just to the E mod n. And so you get 151, 119, 157. That is the encrypted message. You can send this to Megan, and she's the only one that can decrypt it because she's the only one that knows the decryption key, D. And these are called Y, and she raises it to the D mod n. So it's this. These numbers raised to the D mod n go back to the original values of 72, 105, and 33, which you can look up to spell out the message. So it's a little clumsy, but it works. And that's the essence of RSA encryption. Now, of course, this is not secure because these numbers are too small. You could crack it with brute force and other techniques. Real RSA, as we've talked about, needs to use keys that are 2048 or 3072 bits long these days to be secure. But it's the same principle. So there's just some flags to calculate. Or calculate some public and private keys. And this is Q-Ball's keys, so he gets the encrypted message you can decrypt. Yes, the A, Corinne, that's a very good question. I worried about that myself when I first learned about this. Wouldn't it get hard to find primes? It turns out that primes are very thick on the ground. Primes only fall in frequency like the logarithm. I know, I had the same feeling. That's called the gamma function. It's actually a really big thing in mathematics. But the density of primes is a lot higher than you'd think. However, this is why creating RSA keys is a very slow process, because you do have to guess primes and find them, and you might have to guess a few hundred or thousand to find one, but not more than that. That's exactly what I worried about. I worried that the primes would be hard to find, but they are not that hard to find. In fact, you'll do quite a lot of projects here where you find primes. I've got some projects here where you find primes that are 1,000 digits long and longer. If you go down here in the math section, this one here I'll talk about another day, I think, but here you can find prime numbers, and you're going to find them. You'll find a 300-digit prime here. It won't take you long. And you'll find a 100, the first set of companion primes above 100. Primes are so common, you can even find companion primes, which are 2 primes that are only apart by 2, like 3 and 5 are both prime. And 5 and 7 are both prime. Those are called companion primes. And even in the 100-digit numbers, you don't have to hunt too far to find a pair of companion primes. There's a lot more primes than I thought there would be. Anyway, so there's a few challenges here, and you decrypt them. So that's the simplest RSA challenge, where you play with these short numbers that are easy to understand and just gets you used to manipulating these concepts. So I'll stop that one.